All right, so coming back, let me make sure that you got that. All right, so I'm going to replicate the problem that we're going to have. So I'm going to go to the SBT shell, and I'm going to say clean. This will wipe all the files, all the class files. All right, and then I'm going to go here and make this mark directory as sources root. So why do you need to do this? Because if you don't, if you can't run in IntelliJ, you don't have a proper debugger. The only decent debugger is inside IntelliJ, right? You have a debugger inside SBT, but it's command line. It's not very good. All right, so you're going to try to run the tests, because that's the main way we check our code works. All right, and you're going to get these errors. All right, at the point of having run this, as you go here inside target, one strange thing that is happening here is that that folder is not generated. Because this is the problem that I ran into just now with your colleague. And the way to solve it was to try to do the test here. Which works because it's direct interaction with SBT. Oh, it's still not. Oh, we haven't finished. Okay. I think this is there. Just open in terminal. Yeah, you see it's here. As this SG managed folder is here. Oh, and finally I can see it here. All right. So this folder is generated at some point, but it takes a while for IntelliJ to reread the folder and show it to you here. So as you go inside, this main has a blue color. All right, and the blue color means that is a folder for sources, for generated sources. This is a mistake. All right, so you go to this mark directory and you unmark as sources root. As soon as you do that and it gets this crimson color, you will see that the folder underneath is correctly marked as generated sources root, which is what it should be. And now, if you want to go on a specific test, like this one, and run it, so you just want to run one test and potentially debug it, then this will still compile the entire code. It will not just compile stuff that is necessary for that test. It will compile the entire code, right? So if you have any misconfiguration that doesn't allow you to compile some small class, you're still not going to be able to run. And then this, now at this point, you can run the entire code and potentially debug it if you need. Okay, this will give you a lot of grief if you don't get it right now. It will give you a lot of grief later. So hopefully it's captured in the video recording now, and you're going to be able to replicate the steps. Okay. It's a small thing. You're going to get used to it. Okay, let's move on. So how about execution? So we have a virtual machine that is very incomplete. We don't know what it does. We know it has instructions. We sort of kind of understand what it does because we've discussed informally. We also compiled our expressions into that language. So we sort of have some expectations of what each instruction is supposed to do, right? But now let's try to define it formally. So obviously we need a machine state, right? We come in with a program, and as we execute the program, right, we need to execute it one instruction at a time, and as we execute every instruction, we move from one state to the next state. Okay? So we have a notion of transitioning from state to state. What are the important state elements? Well, we're going to have a program counter, or alternatively, the remaining list of instructions. We are in a very nice situation where the instructions are going to be traversed linearly. We never go back. That's not going to last long, right? But currently, we look at each instruction exactly once. We can throw it away, right? We always can think of the program counter as just being the remaining list of instructions. We don't really need that number there. We don't really need to be the list of instructions of being an array. It can be a list. And we have an operand stack, right? We were saying that each instruction pushes or pops stuff from the stack, so we need this operand stack. We're going to call it OS. Okay? So, if we have, for instance, a program counter of 2, we're going to index the list of instructions, the program S, with this program counter is just an index. So S at the current PC, the instruction at the current PC is plus. We start from 0, as computer scientists do in general. All right, and let's define our transitions. All right, so what's above the line is the condition. If the current instruction is LDCI, so when we're saying SPC equals LDCI, right, it means that if the current instruction, the instruction where the program counter points to is LDCI, then do something, or then have the following transition, right? Whatever is below the line is the transition that we execute, right? So we have a precondition and we have the relation or the transition that gets executed. So if our current instruction is LDCI, then from the current state of OSPC, we transition in one step. So this double parallel arrows with an E, we call it a one-step transition. So we transition to a new state where the stack gets prepended with I, right? So I is pushed on the stack, and PC is incremented by 1. All right, the program counter is incremented by 1. Clear? Very simple, right? Similarly, if the current instruction is LDCB of a Boolean, right, we go from the current state of OSPC into a new state where B is pushed on the stack and the current instruction becomes PC plus 1. Yes? If the current instruction is plus, right, we have to be in a situation where there are at least 2 operands on the stack. So I2, I1 must be on the stack. So our state is I2, I1 followed by some OS. OS can be empty, but I2 followed by I1 followed by OS tells us that our current stack has at least 2 elements. Otherwise, we wouldn't be able to perform this instruction. And there's a program counter PC, right? This transitions into I1 plus I2 followed by OS. So notice what happened. I1 and I2 were popped from the stack. The operation got performed. And what goes back is the result. The result is pushed into the stack. So, and then we move on to the next instruction. And then similarly for all the other instructions. Yes? Unary operations are going to have a single operand. All right? And the end configuration, what we call the end of configuration, is one where the current PC indexes the instruction done. All right? And at that point, we wonder what value has been computed. All right? Well, the value that has been computed is whatever is at the top of the stack. But there is an extra condition. The stack must contain only one value. Otherwise, the computation is invalid. All right? So, how do we define a computation by the machine? Well, we take this one-step relation and we compute, or we define, or we use the transitive and reflexive closure of it, right? And we're saying that if from an initial state of an empty operand stack and a program counter containing, having a value of 0, being on the first instruction of the program, if we transition to a state that has a value v at the top, right, and the instruction indexed by PC is done, then that the value computed is v. Okay, clear? All right. So examples. Right? So let's take the program that we have there and we go through a transition, right? So we start from the initial state, which has the empty stack of operands and a PC of 0. LDCI 10 is going to put 10 on the stack. LDCI 20 is going to put 20 on the stack, right? You notice that the PC just increments, goes from 0 to 1 to 2 and so on, right? Then the plus is going to pop 20 and 10 and push back 30, right? Then we're going to put 6 on the stack. So 6 and 30 are both on the stack. Then we're going to perform times. So we're popping 6 and 30, performing the multiplication, pushing back the result. And then we hit done. And at that point, we are in an end configuration. The value at the top of the stack is 180. That is the result. That clear? All right. So let's look at the implementation. I'm not going to use the slides because they still refer to the OCaml implementation. Let's look at the Scala implementation. Right, so we have defined the instructions again. So these we know. And then let's see how we execute. So we need to have a transition. We call it a relation and a mathematical definition, but it's pretty much a function, right? And this is inside the state of the machine. So we don't have a machine per se. We have the state of the machine, and the state of the machine has a transition function as a member. And the transition function returns another state. We don't update the current state because we like to be functional. We like to work with immutable data, right? So the transition takes the current state and gives me a new one, which is the state after the transition. So notice how we implement the rules, right? We pattern match, and the pattern match is a bit more sophisticated now. All right. First of all, as an aside, what you saw on the slide was that we were mixing booleans and integers in the stack freely. All right. This cannot happen in Scala because all of them have to have the same type. They have to be brought to the same type. So we are going to wrap the values in a wrapper that reflects the type. All right, so integers are of the type result int, and booleans are of the type result bool. This result int and result bool have been introduced last time when we looked at the big step semantics. They're the same classes. They come from here, right, and from this one, which was discussed last time. Okay, so notice the pattern matching. So I have a program and an OPD stack, which probably to have been conformant with the slides, I should have put them in reverse order. All right, but I'm not going to look at the program as a number because I was saying we're just looking at each instruction a single time, right? So I'm going to look at the list of instructions and consume one instruction every time. So the program and the OPD stack, I put them in a pair, and then as a pattern match, I can use a really complex type of pattern matching, right? So I say if the program is of the type plus followed by some REST program. REST program can be empty, right? But this means that I have at least one instruction, which is plus in this case. And this OPD stack is one integer followed by an integer n1 followed by an integer n2 followed by REST operands. REST operands could be potentially empty, I don't care. But this writing says that I have to have at least two operands. So if this is the case, my new state, so notice that we're creating a new state, right? This is the name of the class, which is also the name of the constructor. So we're constructing a new state here, which is what? Well, we have consumed the plus. We have finished the plus, right? So the remaining program is REST program, and the result of the plus goes at the top of the stack. So the result of the plus replaces n1 and n2, right? And this is the new state. So I went from the old state into the new state. And this is one-step transition. Okay? Notice this very interesting and very sophisticated pattern matching, right? This would allow us to always to essentially look at cases in a lot of detail whenever we need that, right? We can inspect data structures to whatever level of detail we need. All right, for the unary operators, which are here, notice that we only look at one element in the stack, right? They only have one operand, and we put the result back. Same for negation. We take an int from the stack, we perform the operation, we push the result back. And then for LDCI and LDCB, right, we don't expect anything in the stack. This can be empty, but we are putting something on the stack. We're putting an integer for LDCI, and we're putting a Boolean for LDC Boolean, right? So this is the transition relation. This is one step in execution. Now we have to perform as many steps as it takes to reach the final configuration. Okay? So I think actually is stopped is not a good thing here. I wish I should say is done. So let's rename that. And let's also experience that, right? So if I go here and do a renaming, all instances of this function in my entire code base are going to be renamed. All the relevant ones, right? Because you can have this name as part of multiple classes. It will find exactly the right ones. It's not going to blindly just find every string that is equal to is stopped and replace it. It will just go to exactly the ones that are exactly invocations of this and do it, right? So for instance, if we go here, you can see that is done has been replaced as well. All right, so we're going to have a function called is done, which asks whether the current program has reached the done, right? Now, again, a Scala note. So program.head would be the first element. Program.head would be the first element of a sequence. Program.head may throw an error if the first element does not exist, which is possible when the sequence is empty, right? We don't want exceptions. In general, we don't like exceptions in functional languages. So instead of that, we use head option, which will return an option of the result, right? An option is some, right? Some wrapped around the object. You remember what that is, right? We discussed options. So if I say option 1, I get this is what it is, right? But if I say option of null, I get none, right? So if the result exists, I get it wrapped into the keyword sum. If the result doesn't exist, I get the object none, right? So instead of having an exception thrown, I will get something called none, right? Now, if I write it in this way, I will avoid any exceptions, right? Because I'm sure that this doesn't throw, it might return none. And then I'm going to wrap the expected result, which is done, into an option. And if they're not equal, not equal. None is not equal to sum of anything. And then they're not equal, it's false, right? But there's no exception in that process. If I would write it this way, which is what beginners would tend to do, if I write it this way, there's the danger of an exception when the program is empty. Now the program should never be empty, and if we write correct programs, this variable here should never be empty. But we don't always write correct programs, right? And we don't want exceptions to pop up in our code without a good reason. And therefore, we prefer to write it this way. And then we get a result. And the result is whatever is at the top of the operand stack, provided that we are done. If we try to get a result without being done, okay, then we are going to get an exception. And that's a good kind of exception. That's an exception that is okay to have, because we should be always careful. So with these elements, how do we build the transitive and reflexive closure of the transition? So we have execute here. Execute builds the transitive closure of the transition. We don't use while loops. You might like to write a while loop here. We don't do that, all right? So this is a construct that starts from a initial element. Whatever I put here is the initial element, and keeps applying the function that I put here until forever, essentially. But an iterator is lazy. It doesn't compute the next element unless you ask for it. All right? Now, this is an iterator. Iterators are sequences of values. Sequences of values can be processed with sequence methods, right? So this guy is a iterator. In this iterator, from this sequence, I'm not interested in anything but the last state. Does it make sense? The state of the final configuration, because through execution, what I want is the value that is computed. So I want to reach the last state and not keep anything in the middle. So I'm going to say drop while I'm not done. This means that a computation gets done, but the state is not stored in memory. All right? And keep doing that until while is not done. When it's done, when we reach a state that it's done, right? This function drop while is going to truncate the iterator at that point. Essentially say, oh, throw away the iterator. I'm not interested in anything else. Drop while and then get that one value, right? So this is infinite, but this guy will make sure that gets a finite number of elements out of it. So the fact that it's infinite doesn't bother me. Now, once I get to that state that has a result that is done, I'm going to get the result out of it. So I'm going to take the state and extract just the result. And then to force the evaluation at least one element, which is the element that I want, I am going to invoke next. So this is going to produce the result. All right? This is a very typical way of doing functional programming. It's going to take you a while to internalize it, but I'm not giving you a lot of examples, so try to take this one and understand it, right? If it's difficult to read, this underscore is S is a lambda, right? S turns into S dot transition. This is a state. It's a state that has this type, EVM state, this S, and we're doing S dot transition. The result of this is another state, the next state, right? So because we have a lambda where the argument is used only once, we can shortcut it like this. Same here. So drop while I have a state S where S dot done is false, right? And again, the same thing happens because it's a lambda where the argument appears only once. I can make it shorter. Then once I reach that state, take the state S and give me back the result. Okay, so let's look interestingly at the type. So this is an iterator of states. This is an iterator, so it's a sequence. An iterator is a sequence of this kind of objects. Right? If I look at this expression up to here, it's an iterator of states. And you can check what this iterate is doing. Right? If you just command click on it, you're going to have a short help text here. All right, this comes from the standard library, so it's there. So this is an iterator of EV state. All right, if I extend it to here, this is still an iterator of EV state, but whose first element is guaranteed to be a state that is done. All right. From that state that is done, I take a result. So this is an iterator of results. And from that iterator of results, I take the first element. So since I take one element from the sequence, I'm going to get a result. Does it make sense? Which is what I want here. This is the type that I'm expecting. Okay? So this is a very natural way of building the transitive closure of a relation. We are going to do that a lot. So we're going to encounter the transitive closure of other relations multiple times. Every time we're going to use pretty much this kind of construct to build that. So how would a test look like? So we're going to EVM tests. So you build an initial state, right? As in the slide, the stack is always going to be empty, right? So if we go back here, right, this is going to be empty. And instead of having just a number here, which was convenient for the slide, I have this entire list as part of the state. Yes, and instead of having a number that increases, I have a list that gets shorter and shorter. But the stack initially has to be empty, and this is how we say that the stack is empty. And actually, this type annotation here can be removed to make things easy. And then we call execute on it. All right? Now, our operand stack, remember, has to contain values annotated by type. So it's either result int or result bool. So whenever the result is an int, we're going to have it wrapped in a result int. All right? So that's a possible test. This is how we invoke the virtual machine. Start with program, empty stack, dot execute, that should give me the result. Right? And we can have more complicated expressions or more complicated programs, and then they should all work, right? So if I execute this, this works. Now the interesting thing to do is to put everything together, and what you see is that there's a, oops, no, that there's a green check sign there, which means that everything passed. The more interesting thing is to have a end-to-end test. So we want to start from a string representing our program and go through parsing it, compiling it, and executing the program and getting the result, right? So I have this string, parse it, compile the AST, and then build a EVM state out of it. Right, so this is an EVM state up to here. Execute the machine from that state, and we want a result. All right, so this single test right here essentially puts everything together that we have done for EPL on the side of denotational semantics, on the side of compilation, right? So, yes?
What's the big difference between this one and the one I just talked about last class?
So the last class was an interpreter, essentially did not use a virtual machine, right? Whereas this one is using a virtual machine. So we're taking the expression, compiling it into bytecode, and we're executing the bytecode, right? So instead of having this, right, let's put them side by side. All right, so we have one above, and let's take last time's test, eval test, right? Big step semantics, this one. Right, so last time, this is what we were doing. We were doing eval parse. So we wrote an evaluator, which was an interpreter, right? Eval parse, right? Here we have EVM state compile applied to parse, right? So compile produces bytecode. EVM state creates a virtual machine around that bytecode, and then we can invoke the execution here. So they're fundamentally different, right?
But output is both result true.
Yes, because it's the same program, right? It doesn't matter whether I interpret it or compile it. I should get the same result. Okay, clear? Yeah. Questions? All fine. Okay, if that's the case, let us just scratch the surface on the next topic, which is simple. So now we're starting to talk seriously about programming language. All right, so we're going to introduce computational constructs, right? Not that expressions are not computation, right? But we don't have the ability to do iteration in simple expression, right? So we would like to do that, and all we need to be able to do that is, what do you think? What's the very small step that we need? What's the very small thing that we need to add to our language to make it Turing complete? Yes. Louder?
Go to or an instruction.
I didn't get.
Go to.
Oh, go to. No, I'm not talking about the virtual machine. Is that true? Yes. So we also need conditionals, and but yes, you're right. So if we had Go2 at the level of virtual machine, we would be Turing complete. But at the level of the expression language, louder. You're going to be surprised, but if if else state, we're going to have if then and else statements, but they're less essential. What is louder? Yes, very good. But actually, what kind of functions? I can make them recursive immediately. Okay, so I'm gonna show you, right? Do I need to name the functions? Do I need to have names for the function? So you might want to say yes, because I need recursive functions to do iteration, so I can't do recursion without names, right? But the answer is lambdas are enough. All I need is lambdas, nothing else. Okay? That's a very interesting thing. So let's do an experiment. Let's do an experiment. I'm going to go into Python. Is this large enough? All right. So I want to compute factorial of 1000, which Python is very nice to and there's many ways, to do that. And Python has infinite precision, so it can do it with infinite precision, right? We would get all the digits of 1,000 factorial. So I'm going to allow you to use only the following. All arithmetic is on the table. If else is on the table, and lambdas are on the table. No names. Can you compute factorial of 1,000? And obviously, you might come up with the suggestion of typing all the numbers from 1 to 1,000 and put multiplication between them. But then I'm gonna say do 10,000 or do 1 million factorial, right? And I want to be scalable for that, right? So here's how it's done. So let's start from how we define factorial normally. I'm going to just call it f. And we have a number n, and we say if n is 0, return 1, right? Else. No, I'm going to write it differently. So I'm going to say return 1 if n equals 0, else n times f n minus 1, right? So this would be a very simple factorial, and just to reassure you that I can compute, okay, 990, right? I can compute 1,000 factorial with infinite precision. All right? I can go and change the setting that limits me to 1,000 depth in recursion and compute as much as I want. So now this is my definition. I'm not allowed to use names, right? So I'm going to have to write a lambda. Right? Now, this f must come from somewhere. Okay? So since I can't use the definition, the only place where I can put it is here, right? And if I want to do it this way, then I need arguments here, right? Obviously, the second argument is going to be 990 or whatever, right? What do I put here before the comma? Louder. Itself. How do I get the itself? Identity as in what? I'm gonna take this, Control C, Control V. And I'm missing and because I have two arguments now, I need to put the f here, right? And I'm going to get the result. Okay? So I could show you that actually the if I can put some lambdas. I can come up with some sophisticated lambdas to replace the if. This is enough. At this point, we're Turing computable. This is all we need, right? So that's what we're going to do, right? That's the essential aspect. I can use this pattern for every function, right? And actually, there's a thing called the fixed point combinator that we can define. And then if I am allowed to use one def for my program, All right. It's also known as the Y Combinator, which you know that there is a site. So they chose the name to be quirky. And usually when I ask, do you know what the Y Combinator is? They say, oh yeah, it's that site. It's actually the fixed point combinator for the lambda calculus. All right, so Python. They tend to be hairy and difficult because depending on the language, they're not the same. You can actually use some that don't use recursion, but in general we can take this. Right, so if you were allowed to define one function, to use one named function, right, it would be this. Because now at this point, all right, what I can do is take y and apply it to this function, and further apply it to, what do I get here? Further apply it to 1000, I think 9990. I think it's lambda f, lambda n. Is it? Okay, so I think we have a lot more recursion now. So I'm just going to do 100, and we can do it that way, right? So instead of repeating that function twice, this y actually will do the repetition for us, right? So if we are allowed to do one such to put one name in the function in the language, this is the one you want to choose. All right. Now, because of that, and we're going to go into that soon, we will want to have a such a combinator in the language. So we're going to define our own language with a fixed point combinator, with a recursive combinator that allows us to write recursive functions. All right. So that's what's going to happen next time. And I think I'm already out of time. So let's do this next time. We're going to introduce, besides the expressions that we have, we're going to introduce functions. All right? And then we're going to go through the same path, operational semantics, which is going to be essentially a big step. And then we're going to go to a virtual machine, and we're going to define new instructions that will handle the new language constructs. We're going to see how we compile for it and how we execute virtual machine code. Okay? So this is next time. Hopefully I'm going to be more updated with the course materials by then. I'm going to make the code available at least so you can use it in the lab. Thanks. If you want to stick around, feel free to do so. Otherwise, thanks for coming. See you next time.